we have learned about Faraday's law and Lenz's law. Now we have solved this problem, example 6.4. Let us see it once again so we can understand Lenz's law much better. So what is the direction of magnetic field? It is shown by a cross. That means magnetic field is something like this, that is, it is going inside the plane of paper, and this is cross. It is going inside the plane of paper. Now they are asking whether if this ABCD rectangular loop, this ABC triangular loop, or if this irregular shape loop is moving in or out of this magnetic field, what would be the direction of current in these loops? So now let us take this loop ABCD. So now if we see the movement is such that this is entering in the magnetic field, so that means magnetic field in this loop is increasing. Magnetic field in this loop is increasing. So from right hand rule we know that if a current is clockwise, suppose if a current is clockwise, okay, this current is moving in clockwise direction. So what would be the direction of magnetic field? Same as this arrow, if this is moving clockwise. Now if a current is moving anti-clockwise from right hand rule, so what would be the direction of the current? Direction will be opposite to this arrow. Okay, so it is the direction of this. Now let us see, this rectangular loop is entering in this magnetic field. That means magnetic field in this direction is increasing, and you know that everything try to oppose change in its state. So how will it oppose? It will oppose in reverse direction, because this direction is increasing, so it will oppose in this direction. So what is this direction? This direction is anti-clockwise. So the field in this loop will be, current in this loop will be anti-clockwise in this direction. Okay, so this is anti-clockwise. So this is AC, that means anti-clockwise. Now let us see this loop. So field inside this loop is initially in this way. Now field is reducing. Field is reducing. So how will this encourage this effect? Since field is not increasing but reduces, so it wants a field in this direction, so the effect remains maintained. So it needs a field in this same direction. So in same direction, this is clockwise. So field in this will be in clockwise direction. Current in this loop will be in the clockwise direction. And what about this? Since this is also moving out, so initial field was in this direction, and it will also try to maintain the same field because it is moving out. So in this as well, so current in the loop will be in clockwise direction. So anti-clockwise, clockwise and clockwise. So this is the basis behind solving this example. Now let us go to next example. Next example is 6.5. So first part is, a closed loop is held stationary in the magnetic field between north and south poles of two permanent magnets held fixed. Can we hope to generate current in the loop by using very strong magnet? So they are asking that there is a loop. So here it is not shown, but there is a loop, and this loop is held stationary. Okay, so this, neither the loop is moving nor the magnets, nothing is moving. So they are asking if these magnets are very strong magnets or very big magnets, will we get some kind of current? Answer is no. However strong the magnet may be, current can be induced only by changing the magnetic flux through the loop. So magnetic flux change is a must condition, which is not happening here. Why? Because we are not moving the magnets all this loop. So this is the answer of first problem. Now let us go to second problem. Second problem is, a closed loop moves normal to the constant electric field between the plates of a large capacitor. Is a current induced in the loop? When it is so wholly inside the region between the capacitor plates, when it is partially outside the plates of the capacitor, the electric field is normal to the plane of the loop. In this problem they are asking that we have two capacitor plates, one capacitor plate and another capacitor plate, and we know between capacitor plates we have an electric field. Okay, so this is electric field, so this is positive plate, this is negative plate. Now there is a loop, so we have this circular loop, and this circular loop is moving in this direction, so a closed loop moves normal to the constant electric field. So definitely this direction is 90 degree, that means normal to this electric field, and also the electric field is normal to the plane of loop. So what is the plane of the loop? Plane of the loop is this. Okay, so this electric field is also normal to this. Loop is moving in this direction and the plane of loop is just normal or perpendicular to this electric field. Now this is electric field. So now question is that if this loop is completely inside this electric field produced by capacitors, will there be a current, or if it is half out or half inside, will there be a current? So that is the question. Now let us see the answer. Answer is no. Why? No current can be induced in either case. Why? Current cannot be induced by changing the electric flux. So electric flux cannot induce any kind of current, only magnetic flux can induce the currents. So this is the second question. Now let us see the third question. Third question is, see this figure. A rectangular loop and a circular loop are moving out of a uniform magnetic field region, figure 6.8. Here it is shown. So we have a regular and uniform magnetic field region. This is our uniform region, magnetic field. Now a rectangular loop and a circular loop are moving inside this. In which loop do you expect the induced EMF to be constant? So we are asking if the EMF will be constant or not during the passage of the field region. So if it comes out of this region, so in which loop the EMF generated will be constant. The field is normal to the loops. So now let us see what happens in this case. First of all, they are moving with a constant velocity. They are moving with same velocity. Both are moving with same velocity v. So let us see if the field is only this much. Okay, field is only this much. Outside there is no field, only inside this region there is a field. If you see, if it is completely inside, so there will be no current and no EMF induced inside. Same here. But let us see condition when it is coming outside. So it is now coming outside. So there is a flux change. As soon as this is coming out, there will be a flux change. Flux keep on changing because now this loop is coming out of this region with a constant velocity. But if you see per second change, for let us see if this loop travels this much in per second. So all the areas for this loop, rectangular loop, is same. All the area, this area 1, 2, 3, 4 and 5, those are same for a rectangular loop because its width remains constant. Width remains constant. So same area will travel in 1 second. But now let us see a circular loop. So now it is also moving out of this field. So it is also moving out of this field. Now in first second this will travel this much. Okay, so this is area 1. Next second this much. So area has increased in the same time. Third second the area is further changed. I am not saying it is less or more, but it is changed. In fourth second also change. So in rectangular loop, since its width is constant, so the area will remain same. Once it is getting out, So a change in magnetic field intensity per unit time will remain same. Hence we are getting a constant EMF in this case of our rectangular loop and not constant EMF in case of our circular loop, because every second its area is also changing. Let us see how they have explained this. The induced EMF is expected to be constant only in case of the rectangular loop. In case of circular loop, the rate of change of area. So, rate of change of area, that means how area is changing with time of the loop during this passage out of the field region is not constant. We have seen that area for the rectangular loop was constant per second, but not constant for circular loop. Hence, induced EMF will vary accordingly. So, induced EMF will also change.